Okay, I'm making this video because I think we need a little context here just to make sure we all know what we're doing. This is the normal distribution. um, it's constructed by a formula that has e to the variable power squared, then negated, and divided by some things in it. So this is one type of formula that can make a bell-shaped curve. Okay, you'll see a more complicated formula when you get to your stats class, but it boils down to something like this. So if we're asked to find the center of this distribution, they told us the mean is 55. They want to know the probability of getting a test score between 31 and 43. In stats class, you'll just use a table of values to look it up and approximate it, but you can find the exact value with calculus. And the way we would do that in calculus is find the area under the curve, because these are all probabilities. Okay, the whole thing adds up to 1. So we want to integrate between 31 and 43 here. Okay, so in order to do that, I think there might be even more information. They gave us a standard deviation, so we have to go back. Oh, no, we need the standard. Okay, so what you have to do is convert these to z-scores. Okay, and that's a big reason why I'm making this video, is because you have to have both that knowledge and this stuff I'm about to show you in order to solve this problem. A z-score, if you haven't seen it before, is just this formula right here. So to convert 31, for example, to a z-score, then I'm going to take 31, put that in for x into the conversion function, subtracted by mu, which is 55, and divide by the standard deviation, which is 12. 31 minus 55 divided by 12, so that's negative 2. 31 is negative 2 when we've standardized it, when we change it to a z-score value. Do the same thing for 43. Do 43 minus 55, divide that by 12, so that's negative 1. So what we're going to calculate is the integral from negative 2 to negative 1 of the first 5 terms of this Maclaurin series. Okay, so to find the first 5 terms, we'll do what we've done for Taylor-Maclaurin series before. We think about the derivatives. When it's 0, though, that's talking about the original function. So this is just e, the center is 0, right? So this is negative 0 squared over 2. That's all over 0 factorial times x minus 0 to the 0 power. That's our first term in the Maclaurin series. And then the first derivative, when you take a derivative of this, it's an e with a variable in the exponent, so the derivative is itself, but times the derivative of the innermost function, so times, using the chain rule. The 2 comes down, then gets reduced by 1, so that's negative z to the first power. When you take a derivative of the innermost function, that's negative z. So when we plug that in here, sorry, 1 second. Okay. So this means we're supposed to plug in 0 because it's a Maclaurin series, so it's centered at 0. So if you plug in 0 into all this, you're multiplying by 0, so the whole numerator is 0. The denominator doesn't really matter what it's going to be for the denominator. It's 0 factorial, and this is x minus 0, but whatever, because we've got 0 in here, right? Man, 5 terms is going to be tough, because now we're going to have to use the product rule. Let me pause and make sure I'm going in the right direction. Yeah, we are. So this is the first derivative. Okay. So for the next term, for n equals 2, we need the second derivative. So off to the side here, we'll do that later. This is the second derivative. We need the product rule, right? Because it's the derivative of the first term, which we just did. That's, I'm going to put the negative z out front. Negative z e to the negative z squared over 2 times the second function of z kept the same. So again, I'm just using the product rule. Derivative of the first term times the second kept the same. That's negative. And then it's plus the first term kept the same. So that's e to the negative z squared over 2 times the derivative of the second term. So that's going to be a negative 1. So that's the derivative, the second derivative, I should say. So in our next term in the Maclaurin series, we should be plugging in our center into our second derivative. So plug 0 in here. Luckily, this whole thing becomes 0. And then this 0 up here makes e to the 0 makes 1, so this is just negative 1. So the next term is negative 1 over 2 factorial x minus 0 squared. I can clean this up a little bit. This is still the second derivative, just rewriting algebraically so that we can find the next derivative easily. Okay. Because next we need a third derivative. Okay, so this one needs product rule. 2z times e to the negative z squared over 2 plus the derivative of the second with the first kept the same, so this is going to be z squared. And then this is, we just did that. That's negative z e to the negative z squared over 2. Okay, so we took a derivative of the first term here. It's all this stuff. And the derivative of this term over here is going to be negative z, because it's the same thing we did in the first derivative. Negative z times e to the negative z squared over 2. All right, so the next term is found by plugging in, what are we at? We're plugging in 0 into the third derivative. So this has a 0 times everything, so that's gone. This has a 0, so that's gone. This has a 0, so that's gone. So if you plug in 0, you get 0 again. Then you're going to have to take a fourth derivative. This is pretty brutal. It's not very fun. I need even more room, so fourth derivative. I'm doing this so you don't have to, okay? You can use my result and just roll with it. Okay, so the derivative of this needs product rule again. So the derivative of the, can I type it? Let's do that. Derivative of the first term times the second kept the same. I'm just going to put dot 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 for the power of e, plus the first term kept the same times the derivative of the second. So the second, we've already done that derivative, the e to the negative z squared over 2. We've already done that a lot. So it's negative z e to the same thing for the power. Okay, so we took care of this derivative. Now we need to take a derivative of this. Derivative of the first times the second kept the same, plus the first kept the same times the derivative of the second. So the derivative of the second needs the product rule again. Oh my goodness. Don't do this one without using my video, for the love of mercy. Because, okay, so I got the derivative of the first, the second kept the same, plus the first kept the same, so that's going to be minus z e to the dot dot dot. Oh, okay, I took care of that derivative. The only reason I was able to do it so quickly is because I do this every day. I don't expect you to be able to do this so fast. But this next one, that's going to be a plus because that's minus a negative. We need the product rule, so it's the first times the second kept the same, plus the first kept the same, times the second. Oh, this is too brutal of a problem. I got to check all the other problems and make sure it's not this hard. It's like an important one because the normal distribution is good when you get to statistics to know where that comes from. It gives you more of a reason to believe in what we do with statistics. Okay, there's a lot of math behind your statistics class. Calculus is behind it, but it's not a fun exercise. That's the fourth derivative, assuming I haven't screwed anything up. If you plug in our center of 0, then this term is going to be 2. This term, 0, cancels everything out. This has a times 0. This has a times 0. This does not. So that's 1e. So that's going to be plus 1. And then this is going to be 0. So it looks like if you plug in 0 into the fourth derivative, you get out positive 3. So this is going to be plus 3 over, we're on the fourth derivative, so 4 factorial. And I'm going to pause the video and double check that before I go on. This is the fourth derivative, so now we're at the fourth power. Okay. Oh, I've got it right. So this is the Maclaurin series so far. So to encapsulate it here, or maybe summarize it, This is to the 0, so that's 1. That's 1 divided by 1. This is the 0, so the first term is 1. The second term we said is going to be 0, because 0 times anything is 0. Third term is going to be minus 1/2, so we're going to put minus 1/2, and this is just going to be x squared when you simplify. Then this is plus 4 times 3 times 2, so that's 1 over 8, because the 3 and the 3 up top and the 3 on bottom cancel out, x to the fourth. And then look, the signs are alternating. You've probably seen that from doing Taylor-Maclaurin series already. So I think the next one is, I'm not going to do the sixth derivative. Let's see, that's times, what is that, 2 to the third? That can't be 8 to the third, is it? I think they're to the third power. I'm going to double check for you though. I wasn't able to spot the problem. Sorry, these are supposed to be z's, I just realized. I switched to x for some reason. So 1, 2, 3, 4, 5. These are the 5 terms if you keep going with that pattern. We're not done. That's why I made this video. Okay, so that's the heavy lifting. Hopefully you were able to jump ahead before trying this entirely on your own. Because now we said at the beginning we got to integrate between z equals -2 and z equals -1. So we're integrating the Maclaurin series from -2 to -1, because the Maclaurin series helps you approximate this function, right? This function is really hard to find an antiderivative for, but these term by term are not bad, okay? Because the first term is x, second term is 1 over 6 x to the third, right? Because 3 is times 1/3, yeah. And then this is going to be 5, so that's 40 x to the fifth, and then we got 7 times 48, that's 1 over 336 x to the seventh, and then the last term, I'm going to put it down here, that's 9 times 384, so that's 1 over 3456. That's funny. 3456. And then now you got to plug in the limits of integration, -2 to -1. Okay, so that's it. Once you plug in those limits of integration, go ahead and use technology. I cut the video though because I realized I forgot something. Man, maybe Newton needs to pull this question and redo it, because look, this is an approximation for the normal distribution, but there's another part to it. You got to multiply your whole integral by 1 over the square root of 2 pi. That comes from something we derive in a calculus-based statistics course. That's not part of the original problem statement. I forgot about it. That's part of the complicated stuff I was talking about. That's a part of the formula that makes that bell-shaped curve. So whenever you're done this, you just got to multiply by 1 over the square root of 2 pi. Okay? And that's it. It's a tedious calculation. It's an important one to do though, because we need to believe in what we're doing in statistics when we eventually get there. A lot of the disciplines you're going to go into, engineering, computer science, obviously the biomedical sciences and things like that, they need you to know statistics, and they're probably going to make you take a calculus-based statistics course. So this gives you some background, some extra little bit of practice for when you get to that class.